Hi everyone! Today we're going to talk about laws of exponents. As we start heading toward polynomials, we kind of want to know what these are going to be just to help us along. So the first thing we need to do is find out what the parts of a power are. So everybody kind of loosely uses the term exponents, but what does that mean? Well, an exponent is how many times the base is multiplied. Well, when we look at our parts of a power, we have two parts, a larger number called the base, and the exponent, the smaller number that's kind of a superscripted. And the base is the number being multiplied. So what this really means is going to be 5 times 5 times 5, where we multiply 5, the base, 3 times. So we actually probably do want to answer that question. So that would be 125. 5 times 5 is 25. And 25 times 5 gives us the 125. So that's where we're getting that answer from. So there's two different ways that we can say this power here. I can either call it 5 to the third power or 5 cubed. Some people even say 5 to the power of 3. Either one of those, all of those actually are going to be correct. So let's try some examples, not just solving them, actually just writing them. So the first one is going to be 3 to the fourth power. Hopefully we know that that's going to mean 3 times 3 times 3 times 3, or 3 multiplied 4 times. The next example we want to see is going to be -1 in parentheses to the fifth power. So this is going to be, I'm going to keep this in parentheses, -1.1 times -1.1, whoops, times -1.1 times -1.1 times -1.1. So we see it 5 times. Now the next one we're going to see is going to be a little bit tricky. So a lot of people question what happens when we have a negative with an exponent. And I'm going to have -5/8 to the fourth. So this is going to be a fraction. So when we look at this, we have to know that this means -5/8 times -5/8 times -5/8 times -5/8. So we have that -5/8 4 times. This is going to be different than -5/8 to the fourth. What this means is I'm going to multiply 5/8 times 5/8 times 5/8 times 5/8. And then what I'm going to do at the very end is actually bring in that negative and multiply whatever that product's going to be by a negative. So in this first case, we know that we have an even number of negatives, so our answer is going to end up being a positive number. In this case, we can see that we do have an even number of fractions, but we only have one negative. And we know anytime we have an odd number, our answer is going to be negative. So this is the big difference between when we include a fraction versus when we don't include a fraction. Now we're going to move on to our laws of exponents. And there's actually 9 laws of exponents. The first law is going to be commonly known as the product rule. So what the product rule tells us is that if we have a base with some exponent times the same base, the key here is they have to have same base, that we can just go ahead and add those exponents. For example, if we have something like n to the third power times n to the 20th power. Well, if we look, they have the same base of n, so this answer is going to be n to the 23rd power. All we're going to do is add those two together. If we look at this with numbers, we might see something like 9 to the 17th power times 9 to the 21st power. Again, the bases need to be the same. And because we have the same base, which is 9, we know our answer is going to be 9 to the, we're going to add those two together and get 38th power. Okay? Why don't we try some examples on your own? So 5 to the 6th times 5 to the 2nd, and m to the 5th times m to the 10th times n to the 3rd. Why don't you guys take a moment, try those two out, pause the video, and come back. So hopefully with these, we got 5 to the 8th power and m to the 18th power. Again, all we need to do is add those exponents. So the next law we're going to see is going to be our quotient rule. So quotient, remember, is our answer when we divide, and we can actually see a division here. So this is telling us a to the mth power divided by a to the nth power. Again, same bases. Those are important. So when we look at this, we can see that if we have something the same base, all we have to do is really just subtract those two exponents. So we're going to see an example of that right now. If I have something like 7 to the 5th power divided by 7 to the 2nd power, all I'm going to do is subtract. So I'm going to keep that base, 7, and 5 minus 2 is 3. We're also going to see something a little bit trickier. What if we have something like 5 to the 6th power divided by 5 to the 8th power? Well, our base is the same, so I can go ahead and subtract those. And so I'm going to get 5, keep that base, and 6 minus 8, hopefully we all know, is a negative 2. That's something really important. I'm going to put a star there because we're going to see something that's going to address that earlier and come back. So again, we've seen a couple examples. Why don't you guys try example 1 and example 2 on your own? Go ahead and pause the video. Hopefully, with these two, you got 6 to the 2nd power, and on example 2, you got y to the 4th power. All right, let's move on to our third law, which is one of my favorites because it's super easy to remember. It's our zero exponent law. And this tells us that any base we have raised to a zero exponent. The exponent has to be 0. The answer is going to be 1. So if we have something like 3 to the 0 power, it's going to be 1. If we have negative 5 to the 0 power, it's going to be 1. So no matter what we have, even if it's going to be some kind of crazy fraction, something like x to the 4th over 2 to the 0 power, still going to be, that's right guys, 1. So I'm going to give you guys a moment for you to try 2 on your own. So why don't you guys try example 1 and example 2. Take a moment to pause the video. All right, hopefully with both of these, you got 1. See, I told you zero exponent law was really nice. Our next law is going to be the fourth law, the power rule. And so when we look at this, what we notice is we have our power and we actually have an exponent of that. What that means is all we're going to do is keep that base and multiply our two exponents together. So what does that look like? So it's going to look something like 5 to the 2nd power raised to the 4th power. So there's a couple of different ways we can see this. We know because of our prior knowledge with powers that this really means 5 to the 2nd times 5 to the 2nd times 5 to the 2nd, times 5 to the 2nd, or 5 to the 2nd 4 times. But we don't want to have to go through and multiply all that. So all we really have to do is multiply our two exponents, and this is really 5 to the 8th power. Pretty easy, right? Okay, let's try one more. What if we have x to the 3rd raised to the negative 4th power? Again, all we need to do here is just go ahead and multiply our two exponents. So this is going to be x to the negative 12th power because 3 times negative 4 is a negative 12. Again, I'm going to put a star right here because I'm coming up with a crazy negative exponent, and that's going to mean something to us a little bit later on. Why don't you guys try example 1 and 2 on your own? Again, go ahead and pause the video. Hopefully you guys got 3 to the 20th power and y to the negative 32nd power. Again, some kind of crazy negative happening. So let's move on to our fifth law. And this is raising a power to, oh, it's not. No, it's raising a product to a power property. So what this tells us is anytime we have a times b raised to the nth power, we can go ahead and kind of separate that and make that n an exponent for both the a and the b. So it's going to be a times n times b to the nth power. Not a times n, a to the nth power. Sorry. So if we look at this one, what does this look like? Well, this is going to look like 3x to the negative fourth raised to the second power. So that 2, it's kind of like a reverse distributive property, not really the proper term, but I just like to say that. That 2 is going to be attached to both the 3 and the x to the negative fourth. So this becomes 3 to the second power, and then 4, I lied, x to the negative eighth. Remember, we just saw in our power rule that anytime we have a power raised to a power, we multiply those two together. That's why I got that negative 8 there. And again, if we want to go ahead and simplify this a little bit more, what we haven't seen so far is what does this coefficient really mean? Well, that really means 9. 3 to the second power, 3 times 3. So it would be 9x to the negative eighth. Again, there's something tricky right here going on with that negative exponent, so I'm going to star that just for later reference. All right, why don't you guys go ahead and try example 1 and example 2 on your own. Pause the video. Hopefully you got 4 to the third power, x to the sixth for example 1, and oh, there was no exponent there for example 2. Oops, sorry. Let's go ahead and put one right there now. What if we have a 2? Perfect. So if we have a 2 there, we should get negative 5. I'm going to put parentheses around this, to the second power, x to the eighth, y to the sixth. So I'm going to go ahead and actually simplify that negative 5. We know that that's going to be a positive 25, x to the eighth, y to the sixth. And since I didn't go ahead and simplify that 4, we know this is going to be 64, x to the sixth. Okay? So let's move on to our sixth law. So our sixth law of exponents is raising a quotient to a power. So if we look at this, it's very similar to our fifth law where we have the product to a power. We see that exponent on the outside, so we have a divided by b raised to the nth power. So that really becomes a to the nth power divided by b to the nth power. So that n, kind of like that reverse distributing property, gets attached to both numerator and denominator. So let's go ahead and see an example of that. If we have something like b to the fourth power over 3 raised to the negative second power, this is going to mean b to the negative eighth power, because we're kind of like multiplying those two together, over 3 to the negative second power. Again, we have a negative here that's going to mean something to us in a short bit. Okay, we'll also try another one. What if we have m over n to the fourth p, all raised to the third power? So if we look at this one, what we're going to notice is same thing. We kind of take that 3 and distribute it to everything. So we would have m to the third over n to the 12th, p to the third. And that would be our answer. So I'm going to go ahead, have you guys try example 1 and 2 on your own. Go ahead and pause the video. All right, now that you're back, hopefully you got x to the 6th over 4 to the 3rd. If you did want to simplify that, x to the 6th over 64 is fine. On example 2, hopefully you got 3 to the 2nd, a to the 8th over b to the 6th. And again, we want to start simplifying that. So 3 to the 2nd would be 9, a to the 8th over b to the 6th. Okay? All right. So now we're at our seventh law, the negative exponent law. So we've been waiting to get here. So now we know what it means when we have something raised to the negative nth power. It means it's really 1 over n. Huh? Okay, so if we look at that, something like x to the third power raised to the negative second power. First of all, we know from our power of raising a power to a power property that this is going to be x to the negative 6. So now we see that we have a negative exponent. But what does this really mean? Usually when we write exponents, we actually don't like to have negative exponents. Most directions you'll see say rewrite using positive exponents only. So how do I write this using a positive exponent? I would make this 1 over x to the 6. And I'm done. All right. Want to try one more? Okay. So let's see one with an actual number. So we're going to have 3 to the negative fourth power. So again, what this means is, really quickly, I don't know why I put this in parentheses, sorry, 1 over 3 to the fourth power. So now we don't have that negative exponent. But again, we want to go ahead and simplify this. So we know that 3 times 3 times 3 times 3 is going to be 81. So this will simplify to 1 over 81. So we are working with positive exponents now. All right? So why don't you guys try example 1 and example 2 on your own. Pause the video. Hopefully you got, on example 1, 1 over m to the third. And for example 2, hopefully you got 1 over, I'm not quite sure if you made this negative 3 to the second, or if you took the time to simplify, which hopefully you did, and you got 1/9. Okay, so moving on to our next law, the 8th law. There's not really a title for this, but it kind of goes along with negative exponents as well. So what we notice is this time it's not a negative, just a negative 1 base. We have a quotient. So this is telling us that if we have a divided by b to the negative nth power, that really what happens is we can go ahead and flip that numerator and denominator around, find that reciprocal, and multiply it times the nth power. So what is that going to look like? Well, let's see right now. So if we have an example of that, that's going to mean something like y to the fourth over 3 raised to the negative third power. So really quickly, I'm going to go ahead and just flip that around, so I get 3 over y to the fourth to the third power. And then we know, because we just saw our power of a quotient property, that this really means 3 to the third power over y to the 12th power, which will simplify, because we do want to simplify that 3 to the third power, to 27 over y to the 12th power. Whoops. All right, so why don't you guys try example 1 and example 2 on your own. Go ahead and simplify that. Pause the video. Hopefully, on the first example, you got 8 over x to the third to the negative second power. I lied, to the positive second power. And when we simplify that, we would get 64 over x to the 6. We always want to try and start getting everything into its most simplest form. On the second one, hopefully we got 3 over x to the fourth to the second power, which again, we want to simplify that as best as possible, would be 9 over x to the 8th power. Okay, so now we're moving on to our last law. And it kind of deals with negative exponents also. It's kind of the reverse of the 7th law, where the 7th law told us we have a to the negative nth power, which is 1 over a to the n. Now we're kind of starting with the 1 over and making it negative. And just like we saw in the 8th law, all we needed to do was flip that reciprocal. That's what we're going to do right here. We're kind of going to flip the a and the 1, and it's going to turn into a positive exponent once we get our new base. So if we want to see an example of that, we have 1 over 2 raised to the negative 5th power. So if we want to write this with our 9th law, we would just write 2 to the positive fifth power. Again, because we want to simplify this, we know that this is going to be 2 times 2 times 2 times 2 times 2, or 32. Okay? Go ahead and try example 1 and example 2 on your own. Take time to pause the video. Now that we're back, when we simplify these, hopefully we got 5 to the second power, or we're getting used to simplifying 25. And for our 1 over 8th to the negative third power, hopefully we got 8 to the third power, or 512. Should have known that, sorry. So now we're going to put it all together. So we saw all 9 laws of exponents. What does that mean? Well, when we have a compound problem where we have lots of stuff going on with our steps, it kind of helps to know those laws of exponents. So if we look here at example 1, the first thing we're going to do is go ahead, and we know that that negative 2 is going to do that little bitty reverse distributive property thing, and it's going to hit every single term there. So we're going to have a to the negative fourth, b to the negative second, c to the negative second, and d to the negative sixth. And then what we learned was anytime we have a negative exponent in our numerator, pretty much it goes to the denominator. Anytime it's in the denominator, it becomes a numerator. So we're going to go ahead and switch those around. So our a to the negative fourth power is going to go to our denominator and be a to the positive fourth. Our b to the negative second also going to our denominator, becoming b to the positive second. C to the negative second power moves up to our numerator. Remember, this is where we just do all of that flipping with the reciprocal. And d to the negative 6 moves up to our numerator and becomes d to the sixth power. So this is going to be our final answer. I know that was confusing. We're going to try another one. Don't worry. So again, this time, hopefully it's not going to be as bad. We do have some numbers incorporated, which means we're going to have to do a little bit of simplifying there at the very end. So let's try this one. First thing, that raising the power means we're going to go ahead and multiply. So we would get 2 to the negative third power, a to the negative sixth, 3 to the negative third, and b to the negative 12th. Because we have these negatives, remember we have to flip them. So I'm going to flip my 2 to the third and my a to the sixth, and those are going to become positive. And I'm going to flip my negative 3 and my b to the negative 12th. So we're going to have 3 to the third and b to the 12th. But we're not done yet, because we have to remember that whenever we have our numbers, our constants raised to a power, that we're going to go ahead and simplify. So 3 to the third power means 27, b to the 12th, over 2 to the third power is 8, a to the sixth. 27 and a don't have anything in common, otherwise we would have to simplify that, and this is going to be our answer. So why don't you guys try? And remember, be very careful with the negatives, because we only do the reciprocal or flip them up to the other part of the fraction when they're negative. Why don't you take time to do this problem? Pause the video. Okay, hopefully you got the final answer of 125 b to the sixth over 64 a to the ninth c to the ninth. Let me know how you feel about that.